we have two curves. One is y equal to x plus log of x minus 2 and another is y equal to x minus log of x minus 2. And let us try to illustrate the way of finding whether these curves are concave or convex with respect to x axis. In case of concavity and convexity, we have two terminologies. We sometimes say that it is concave upwards and convex downwards, and sometimes we say that it is convex with respect to x axis and concave with respect to x axis. Now let us illustrate the idea of concavity and convexity with respect to these two typical curves, and we will go on illustrating whether or not these curves have a point of inflection. And with this idea, we will try to draw these curves also. So this example helps us to illustrate the idea of concavity, convexity, as well as the idea of point of inflection. And you know what is point of inflection? Point of inflection is a particular point on a curve at which we have concavity to the left hand side and convexity to the right hand side. That means while crossing that point, a curve changes its nature. So at this point, if we draw a tangent, we have in the left hand side in this part of the tangent and right hand side in the other part of the tangent, the curve lies. So this is called a point of inflection. And in case of concavity and convexity, we have hold the curve lying to the same side of the tangent. And we know the test of concavity or convexity. Whenever d2i dx2 is positive with respect to a axis or point or a position, we say that it is convex with respect to that point. Now let us differentiate these two curves. What is dy dx? Dy dx is in the first curve, it is 1 plus 1 by x minus 2, and in the second curve it is 1 minus x minus 2. Okay, and from this we have d2i dx2 equal to minus 1 upon x minus 2 whole square in case of the first curve, while plus 1 by x minus 2 whole square in case of the second curve. Right? This is the first curve and this is the second curve. And we know that whenever d2i dx2 is positive, we have y equal to fx convex wrt x axis, and we may write that it is concave upwards. Isn't it so? They are equivalent. Always remember, whenever it is convex wrt x axis, we may say that it is concave upwards. We know that. You should remember this. Now just see that in case of the second curve, we have this feature because this is always positive, and the opposite in case of the first curve. So it is always concave upwards. Now just see that x is always greater than 2 in case of this curve. X is always greater than 2, strictly greater than 2, because the domain of definition of these two curves is x greater than 2, isn't it? So actually the domain of definition should be written as r minus this, isn't it so? We should write it like this, open closed interval. That is the domain of definition, r minus infinity to t, 2. Since x equal to 2 is undefined and x less than 2 is also undefined. Okay. So this much for concavity, convexity, and what about point of inflection? The point of inflection is given by the rule y equal to 0, but not necessarily always. It may so happen that we have a point of inflection at which we don't have y2 equal to 0. Let us illustrate with this curve. Okay, so I am wiping it out and we are proceeding to find out the picture of the curve. According to our theoretical knowledge of concavity and convexity, we have seen that y equal to x minus log of x minus 2, whose domain of definition is x strictly greater than 2, is concave upwards and or convex w at the x-axis. And what is dy dx? Dy dx is 1 minus 1 by x minus 2. So at x equal to 2, x is always greater than 2. So we can write it as this. Delta is a very small positive number. Then what is x minus 2? X minus 2 is delta, and this becomes dy dx tends to 1 minus 1 by delta. What is this value? This value tends to minus infinity, as we all know, isn't it so? And now let us move on to plot only. Here let us plot only 2 points. One is x equal to 3 and another is x equal to 4. Let us plot only these 2 points. Just see that at x equal to 3 we have y equal to log 1 is 0, 3, isn't it so? And what about x equal to 4? You don't need a calculator. What is it? The value of y at x equal to 4? It is 4 minus log 2. It is 4 minus log 2. Approximately it gives us the value of 3.8 or something like that, something less than 4. And at x equal to 3 we have log 1 0, so y equal to 3, and this suffices. Why? Because we already see that at x equal to 2.5 we have y equal to 2.5 minus log 0.5, so it becomes 2.5 plus log 2. So with this idea we can easily draw the picture of the curve and conclude why it is concave upwards always. Can anybody tell me at which point we have parallel tangent to x-axis to this curve. So dy dx is 0. Whenever dy dx is 0, we have we have 1 equal to 1 by x minus 2, that means x equal to 3. So this is the point at which we have tangent parallel to x-axis. So all these informations taken together we can plot or draw the curve easily. How? Let us say this is x equal to 2. So then this is 4 and this is 3. So at x equal to 3 we have y equal to 3 and x equal to 4 we have something, and at x equal to 2.5 we have almost parallel here, and at x equal to 2 we have the curve y tending to infinity. So the curve will be like this, and this is the tangent at x equal to 3 which is parallel to x-axis. So the curve will be always, we don't know about this part. Actually this curve becomes very stiff here and almost straight line here. Anyway, we can easily decipher with these 3 points 2, 3 and 4 that the curve is like this. Isn't it so? And it is always convex with respect to x-axis or concave upwards. So that is the basic idea of concavity, convexity as well as point of inflection, and this curve has no point of inflection because it do not have any part on the other side of this tangent parallel to x-axis. Okay, another example, a very good example to illustrate this concavity, convexity as well as point of inflection is this one, a very complementary example. Y equal to cos x plus sin x into e to the power x. This is a very typical example. Why? Because if we take dy dx, it becomes cos x minus sin x into e to the power x plus e to the power x into cos x plus sin x. Isn't it so? Because derivative of sin x is cos x and derivative of cos x is minus sin x, then e to the power x is held constant, and when you take the derivative of e to the power x, this term is held constant. So dy dx is like this. What about d2y dx2? Just see that in case of d2y dx2 we have the first term like this. When e to the power x is taken derivative, this is held constant, and then the derivative of this comes into effect. Cos x is minus sin x and sin x is plus cos x, makes it minus cos x. What about this one? When e to the power x is derived, taken derivative, it gives e to the power x only, and when cos x is taken derivative, it gives minus sin x and sin x gives plus cos x. So this is cos x minus sin x. So these two terms add up and these two terms cancels out. It is very easy to check, and d2y dx2 becomes this. So d2y dx2 becomes this, and since we know that e to the power x cannot be negative, so this is positive or negative according as cos x is greater than sin x or cos x is less than sin x. So these are the two conditions. for concavity and convexity with respect to x-axis. Whenever we have cos x greater than sin x, it is convex with respect to x-axis or concave upwards, as we have learned, and whenever we have cos x less than sin x, then we have d2 by dx to negative, so that we have concavity w at the x-axis or convex upwards. Okay. So, when is cos x greater than sin x? Let us ponder over it. When is cos x greater than sin x? Cos x is greater than sin x for the portion 0 to pi by 4 and 5 pi by 4 to 9 pi by 4. Cos x is greater than, let me wipe out this and write here, cos x is greater than sin x for 0 to pi by 4, actually inclusive, greater than equal to, if we would have written it like this, then we have this, and in 5 pi by 4 to 9 pi by 4. This is the zone in which cos x is greater than sin x, and in between 5 pi by 4 to pi by 4 to 5 pi by 4, we have cos x less than sin x. Sorry, pi by 4 to 5 pi by 4. Okay. So, these are the zone, you can easily find out it. And what about dy dx 0? When is dy dx 0? d2 by dx to 0 is at x equal to pi by 4, you can see it, and that is where it is crossing. At pi by 4 it is coming out from concavity to convexity. So, point of inflection is at x equal to pi by 4, and it is clear from here. So, if you remember this, that convex for this zone which is 0 to pi by 4, and concave at this zone which is pi by 4 to 5 pi by 4, and we have at 5 pi by 4 also cos x equal to sin x. So, we have, isn't it so? That is also a point of inflection, 5 pi by 4. We should have the picture of cos x and sin x drawn in 0 to 2 pi limit if one wishes. This is y, which is cos x or sin x, and we can draw the curves. At 0 we have cos x equal to plus 1, and at 2 pi, say this is x equal to 0, isn't it so, the origin, and let us take it as x equal to 2 pi. So, we have minus 1 here. So, cos x starts from here. Let us also mark it as pi by 2, this as pi, this as 3 pi by 4, sorry, 3 pi by 2 I should write. This is pi by 2, this is 3 pi by 2, and pi by 4 is something here. So, at pi this becomes minus 1, at 3 pi by 2 this becomes a 0, and at 2 pi this becomes again plus 1. So, this is the curve of cos x, and if we draw a curve of sin x, we have 0 here, at pi by 2. This is the curve of sine. So you have curve like this, isn't it so? So in this zone we have cos x greater than sin x. And after that sin x is greater than cos x up to this zone, up to this point, isn't it so? In between we have sin x, which is this curve, greater than cos x. And from this zone again we have cos x greater than sin x. So from 0 to 2 pi we have this type of breaking.